This tutorial shall show you some packages and functions that we use often when we use Python for science, for analysis, and for speech sounds. It's probably much better if you walk through that tutorial on your own, but feel free to watch this video, and it really shall not be something that you need to memorize. It shall just be some examples, what you can do with Python, and to show you that Python is very powerful with just a few functions. So first of all, to use sound files with Google Colab, you need to upload the sound files that you want to use. You can do that with these two snippets of code here, or you can also upload it by clicking here on Files. And then you have an upload button here, and you could upload a sound file. What I have uploaded and will use in the following is this LJ001. This is the very first WAV file of a large speech database where a woman reads text for 24 hours. That's why it's often used for text-to-speech applications, because you have lots of data from one speaker. So to upload it, just click here, upload, and choose your sound file. Make sure it's not a sound file that's too big. Ideally, it's speech, but it doesn't really matter. After you've uploaded your sound file, let's go to the code, and let's go to this snippet right here. First of all, I import several packages. The first one is the module pyplot of matplotlib, and I import that as PLT. That's also a common naming convention. This is basically a package that's used for plotting, and it's called matplot because MATLAB is quite good for plotting, so that emulates those MATLAB functions. At least that's what I think, why the name comes there from. librosa is a package that provides some basic functions for sounds. SciPy is a very large package for everything of scientific Python. Quite often we just import only SciPy.signal, and we import that as SS. But for the sake of demonstrating how packages work, I just use import SciPy. And you've already learned the package NumPy. So here I define a file name, and make sure if you've uploaded another WAV file that you adjust this file name here to the file that you have uploaded. And then the first two commands, so to load a sound file that's on your computer, if you're working on your computer, or that's here in the cloud in your files directory, if you're working with Google Colab, then with the load command in librosa, you can load that WAV file, and it gives you the signal, and it also gives you the sampling rate, the sampling frequency. So this has this gives us two outputs, and we use both the signal and the sampling frequency. And then we use the matplotlib package to just plot that signal. That produces a plot. It's a simple speech signal. And there are also easy commands to directly play this sound file within Python. Of course, you could just play it in your Explorer. That would work as well. And that's in a package from IPython. So I import IPython .display. And I think this function is new for you in this form. So when I use from IPython.display import audio, then I import the audio function only from the package IPython.display. And then I can call the function directly just by using audio, and I don't need to write IPython.display.audio. And I do the same for display. I'm not sure why I do this here. Probably that it works. This is a good example. I don't know what I'm doing. I just wanted to play a sound file in Python. So what I actually did is play sound Python, enter that to Google, and it will give you some code snippets that work. So I just copied that. So then I call that audio function. It needs the file name that we've just defined right here. Then we say autoplay equals true. again, I've just copied that from Google, and then I can play that sound file here in my browser, which I won't do because I know that it works, and I hope maybe we'll just get some feedback or so. But if you use the same sound file, then you should hear the woman talking. Okay, some examples for the SciPy package. It's really easy to, for example, filter a signal in Python. So with these 2 lines of code, I apply a bandpass filter to that signal that I've just loaded to my speech signal. So the first function that's used here is scipy.signal.butter, because it's a Butterworth filter. I tell it the order of the filter. The lower the order, the less distortions, but also the less steep the slopes of the filter. So actually some content below 500 and it still is medium, because it's a rather flat filter of order 6, but steep enough for most applications. I want my cutoff frequencies at 500 Hertz and 1000 Hertz. So this bandpass goes from 500 to 1000. And the Butterworth filter can be anything: low pass, high pass, band stop, or band pass. So I need to tell that function that it shall be a band pass, and the sampling rate shall be the sampling rate that we've seen above. So this function wants a variable that's fs in the function. I call it by name, and I also call it the same name in my own code. So that's why fs equals fs, but I need to pass that so that I don't get the default of this function. And then in the second line, the actual filtering is done. That first line just created the filter with the filter coefficients. So this is again a function of that scipy.signal package, and this applies to the Butterworth filter that I've just created to variable s, the signal in s, and the output is a signal called y, and you could already see the signal s in your variable explorer. So signal s, it's basically just a very long array of numbers. So sampling rate is 22,000. So this is 212,000, so almost 10 seconds, 9 seconds, and a bit. And if you want to plot that signal, it would be a bit more beautiful to have meaningful axes here, and that's what I want to do here. So I say the time axis shall just an array of the length of y, which will be the same length as s, these 212,000 and some values. But I don't want it up to 212,000. I divide it by the sampling frequency so that the unit is now seconds. Then I plot again my signal, and now I use t as the x-axis and y as my actual signal to plot. So this is kind of plot x versus, or y versus x. And I label the x-axis and I label the y-axis, and then I use plt.show, which is sometimes not necessary, but it also deletes some unwanted things like this thing here. So if you don't use Google Colab but Spider or other things, then you might actually need that show of the matplotlib package. So let's run it and then recap what we just did. So we applied a bandpass filter to our speech signal, and we made a beautiful plot of almost 10 seconds with axis labels. And because it's bandpass filtered, it looks a bit different even in the time domain. And of course, you might also want to listen to it by just creating another file and then play it, and we will come to that later. But first of all, let's look not just in the time domain, but let's create some spectrograms. And again, this is very easy in Python, nothing to memorize. If you want to plot a spectrogram, then Google for it. If you know that SciPy package is good, then Google for SciPy spectrogram. If you don't know that yet, then Google for Python on spectrogram. It might lead you to another package that does more or less the same thing. And in SciPy, It doesn't not necessarily directly plot it, I think, but it gives you three variables. It gives you frequency, time, and the actual spectrogram, and then we can do a three-dimensional plot using the peak color mesh function of matplotlib. And again, I want to label the axis. So you might get a feeling on how this programming work is done. Those two functions are nothing that you memorize, but once you use a function several times, like labeling x and y axis, at some point you memorize it. And the other time of coding, you Google most of the time. So this is a spectrogram of a speech signal. Sampling rate was 22,000, so frequency range from 0 to 11,000, and most of it happens up to 2 kilohertz. I put at the high frequencies too. So we did a bandpass filtering of that signal, which is in variable y. So we just plotted what was in variable s and created a spectrogram for that. So let's do the same, except the same for variable y, and put that into a capital Y variable, and then just plot that on capital Y to see if we've done what we actually wanted. And this sounds correct, or looks correct. We applied a bandpass from 500 hertz to 1000 hertz. So now we have the content in here. And so that bandpass function that we had right here seems to do something sensible. And finally, we could simply write our sound file and play it. And this is done, I think, most easily with a package called sound file. But there exist many packages probably that do exactly the same. So I use a sound files function called write, and I give it a file name. I give it my array of numbers basically, and the sampling rate, say saved it in WAV format with 16-bit, and then I've saved it, and I can play that too. And now it also occurs in your file tabs in Google Colab. So this tutorial is nothing to memorize. It shall simply be the take-home message, and Python is quite powerful. And the way you program with Python is really, you Google most of the time. When you want to apply a bandpass, then Google for bandpass Python, or Google for bandpass SciPy. And it will give you solutions that you just need to adjust for your specific problem. So in these few lines of code, we have loaded a signal, we have plotted it in a time domain, we played in audio, we have converted it to a spectrogram and plotted the spectrogram, did some labeling with the axes. So that's how coding is basically done. When you do an ANOVA or whatever, then you don't worry about the mathematics behind it. And the same here, when you plot something, you don't worry about the communication of your code to your monitor. So you just use the packages of Python, which is a quite high-level programming language. And you make some progress quite quickly. So that's basically it. Look through that code on your own and play a bit with Python, and but the best way really is to have your own project. So during the lectures, do all the exercises that really helps you to become proficient in Python. And when you have a dissertation, then try to do as much as possible on your own in Python. Try to understand code that others have written, because this will really make you proficient in a programming language.